Hello, I hope you are doing well. My name is Blake Smerigan, and I'm going to be talking about the anaerobic digestion of food waste using iron-rich electrocoagulation sludge as a co-substrate. Waste management is an ever-increasing problem in modern society. This is especially apparent in small and decentralized areas like rural towns, research bases, and isolated locations. Two major sources of waste are wastewater and food waste. These wastes are very high in accessible organic material and therefore cause excessive pollution. One way to reduce the pollution caused from these sources is anaerobic digestion. Anaerobic digestion breaks down these wastes to produce biogas. This biogas is typically composed of methane, carbon dioxide, and hydrogen sulfide. The methane can be collected and used as an energy source. However, hydrogen sulfide, a highly toxic and corrosive gas, must be removed from the methane, which is a difficult and expensive procedure which reduces anaerobic digestion's economic feasibility. Food waste proves especially challenging for anaerobic digestion due to being highly acidic, having a complex structure that is hard to break down, and having sulfur contained in protein that increases hydrogen sulfide production. So this study looked at the co-digestion of food waste with an iron-rich blackwater electrocoagulation sludge which was collected from our pilot wastewater treatment facility as a way to facilitate the removal of hydrogen sulfide. This was done with a hydraulic retention time of 10 days, which was lower than the typical HRTs used in anaerobic digestion of 15 to 20 days. So we tested this by adding food waste and EC sludge to the digesters based on the amount of total solids. The different conditions we tested were EC sludge only, food waste only, a 1-to-1 ratio of food waste to EC sludge, and a 2-to-1 ratio as well. All digesters were stirred continuously at 150 RPM for the 42-day operation. Also, each digester was fed 100 milliliters of their designated substrates every Monday, Wednesday, and Friday. This was done inside a glove box which was purged and filled with nitrogen, which you can see in the image in the methods box. To measure the composition of the biogas that was produced, gas chromatography was performed each Tuesday to measure the amount of methane, carbon dioxide, and hydrogen sulfide in the headspace. Also, each Wednesday, sCOD, sTOC, attain, TP, total solids, and total volatile solids were measured. All compositions were run in duplicates at both the mesophilic 35 degrees Celsius condition and thermophilic 55 degrees Celsius. So for our results, we found that the mesophilic 1-to-1 ratio reactors produced the most biogas and had the fastest production rate once steady state was reached. The next highest amount was in the mesophilic 2-to-1 ratio. All the thermophilic reactors were outperformed by their mesophilic counterparts except the EC controls, which were within 500 milliliters of each other. As for the methane concentrations in the biogas, the EC sludge controls had the highest concentrations, followed closely by the mesophilic 1-to-1 ratio. Both food waste conditions had failed by week 3 in producing very little methane, most likely due to the highly acidic conditions in the reactors, making them uninhabitable for the methane-producing archaea. By week 4, all the reactors except the EC sludge controls and mesophilic 1-to-1 ratio had failed. This can also be seen by looking at the COD concentrations in the liquid digest state. COD was decreasing all the reactors until week 3, where the failed reactors began to increase back to their starting levels or even higher. When looking at the total methane production for each reactor based off their total biogas volume multiplied by their methane concentration, the mesophilic 1-to-1 ratio produced the most methane. For the hydrogen sulfide concentrations in the reactors, extremely high levels were observed when the reactors were in the process of failing. This can be observed in week 4 for the mesophilic food waste control and 2-to-1 ratio, as well as the thermophilic 2-to-1 ratio and the 1-to-1 ratio beginning to fail. Once a reactor had completely failed, it began producing less hydrogen sulfide and more carbon dioxide. Unfortunately, we were not able to measure the hydrogen sulfide during the 3rd week of operation, which is believed to be when the thermophilic food waste failed, resulting in an underrepresentation in the amount of hydrogen sulfide produced by those reactors. The mesophilic 1-to-1 ratio had very little hydrogen sulfide produced over the entire course of the operation. Overall, the mesophilic 1:1 ratio reactor performed the best, producing about 7.8 liters of methane while having the highest sCOD to methane conversion of about 30%. Also, the amount of sCOD in the liquid digestate reduced to about 5.6 grams per liter from the original 10 grams per liter. We also observed a decrease in total nitrogen in all the reactors, while the total phosphorus levels decreased in all reactors which did not fail. So the conclusions we found were that the food waste was extremely difficult to work with as we expected. Both food waste controls in 2:1 ratios failed shortly into the experiment, and all thermophilic reactors that contain food waste failed. We did find that iron-rich EC sludge was able to make the digestion of food waste more viable. The mesophilic 1:1 ratio outperformed both mesophilic controls in almost every aspect. We concluded that the co-digestion was able to remove TP, TN, COD, and TOC, making the waste less harmful to the environment. We also found that the mesophilic conditions outperformed the thermophilic conditions for the co-digestion, and that the 1:1 ratios outperformed the 2:1 ratios. Some ongoing studies for this experiment will be the DNA analysis of the reactors to find the type of bacteria and archaea, as well as the ratio of the amounts between them. Further testing will also be done with varying the amounts of total solids in the reactors, as well as further shortening the hydraulic retention times for them. I would like to give a special thanks to the Department of Defense for funding this research. Also, thanks to Sibel for helping to guide me as I have worked on this project. You taught me so much about planning and running an experiment. Thanks to Adam and Gus for all their contributions. It would not have been possible to manage this project without the help you both gave me. Finally, thanks to Dr. Liao for mentoring me on this project. It was a great learning experience, and I thoroughly enjoyed my time working on it. Thank you for listening.